Le queremos dar la bienvenida al doctor Robert Dunbar. El doctor estudió geología en 1975 en la Universidad de Texas. En 1981 se doctoró en oceanografía en la Universidad de California, San Diego. Fue director fundador del programa de posgrado interdisciplinario en medio, ambiente y recursos. Fue director del Earth System Program de la Universidad de Stanford, donde ha sido profesor de ciencias de la tierra desde 2008. Sus temas de investigación incluyen cambio climático, oceanografía, ecología marina y bioquímica. Se ha comprometido con la creación de políticas públicas dirigidas a solucionar las principales problemáticas de los océanos. Su grupo de investigación se dedica a estudiar pasado y presente de cambio climático polar, entre otros temas. Le damos las gracias al doctor Dunbar por haber aceptado venir a México y venir a este seminario, y los dejamos con ustedes, con él, para que nos dé su conferencia magistral. Gracias.
Gracias. Bienvenidos. Muchas gracias por su atención. But I'm very sorry that I don't speak better Spanish. I understand a fair amount, but sometimes when I'm speaking, I'm told I speak like a child. So I'm going to give this talk in English. Maybe once in a while I'll break into a little riff of Spanish, but I've also worked pretty hard to make the slides pretty straightforward, and I think it'll be easy for everyone here to kind of follow along. So first off, I'd love that you're doing this program in sustainability. At my university at Stanford, 3 years ago, we began to revision the university. And the president asked everyone to submit proposals. And the proposals came in from all over campus. Some people wanted to be able to bring their dogs to work every day and have dog parks. Some people wanted a major reorganization. Some people wanted to get rid of the president. All of these came in, and he threw some away and kept others. And by this process, a new major program in sustainability became number one. And the university had already been raising funding from donors for 3 years. And so then they said, okay, this is what we're doing. Here's $1 billion, do it. So we're now in the middle of creating a new school of sustainability that has faculty from engineering, from ecology, evolution, all of the earth sciences, the marine sciences, and they'll all be in a single school, right, for the first time. And we think that's different than what's being done other places. We are trying to focus on problem solving as a major component of the sustainability school. So this is a group that I founded at Stanford, a center for ocean solutions. It's to take ocean research and apply it directly to problems. Okay, so launching into the main part of the talk, I'll just say a little bit about who I am and what I'm interested in. So I study climate change, but I work in the ocean. The oceans are the largest liquid water reservoir on the planet. This is the volume of the ocean scaled to the volume of the Earth. If you removed all the oceans from the basins, it's a small sphere, but this tiny little dot here is fresh water. And you can't even see the tiniest dot that's the water vapor in the atmosphere. And so this is where all the heat goes, right, and comes from. That's how our climate system works right now. That large amount of ocean water absorbs and releases heat. Right now we think over 90% of all of the heat of global warming, it's in the ocean, and it'll stay there for centuries. The oceans also absorb and release CO2. That has big impacts on coastal zones. And the oceans also receive water from the melting of ice sheets. So I do a little bit of work in all of those areas, but today, let's go this way. Today we're going to talk about the past 500 years of climate variability in the Pacific, and then a little bit about carbon chemistry. And then this is my lab group of of people that go into the field, a mixture of staff and postdocs and graduate students, and I take a lot of undergrads into the field as well. So this is where we go all over the world. Each one of these dots is a place where we've studied a climate change impact or a climate change record somewhere in the ocean. And there's not much in the Atlantic. You know, I did some work in the 70s here in the Gulf of Mexico, but the Atlantic is much less important for governing global climate change than the Pacific, right? This is the big kahuna. And when we have sites like this, you know, that span this warm water area, okay, there we go, that span this warm water area, then what we're trying to do is see how does this hot water area expand and contract through time? And what does that do to storms? And it expands and contracts a lot, actually. So the other thing that I work on is this fundamental boundary condition, the difference in temperature between the hottest part of the planet, oceans, and then the coldest oceans on the planet. And that controls everything, strength of the winds at all latitudes. So that's a fundamental parameter. So we collect samples and go back through time at all those locations. I've been able to figure out how to teach in the field as well. About 80% of my teaching occurs outside and in places where nature is pretty raw, pretty pristine, and the pedagogy involves how the human enterprise intersects with nature, right? So it's fishing, logging, forestry, agriculture, ranching, energy, water. You know, these are all areas where there are complex relationships. And you'll find when you pursue a program in sustainability that you have to understand the coupled human-natural systems. And it includes economics, psychology, sociology, political science. All of these things have to be brought in to the solutions. And so there's a pretty good pedagogy now, and my next class is going to happen up in Nepal in next September. I do take students into the field. I've been able to take over 100 students, mostly undergraduates, to Antarctica, mainly because I've been working there a very long time. But if I take 3 students a year, it adds up. And we go out camping in places like this, and I also go up into the mountains in Patagonia. So this talk has 3 parts. I'm going to say first a few things about climate change impacts on tropical coasts with some references to Mexico, where Mexico has a few special things to worry about, like storms. And then a short segment on methods of examining past tropical change. And you guys are doing some of this on coral cores that you've collected here in Mexico through the Institute. And then I'll say a little bit about carbonate system analysis in the coastal zone. So this is one of the latest compilations of temperature. It's a global average temperature, land and sea, and it goes back to the year 1850. So there's 170 years of temperature. And we now know enough about this year. I mean, we only have 1 more month to go, but it looks like it's going to fall about there. It could be down a little bit, it could be up a little bit, but we know it's going to be the 2nd warmest year on record. It's just how it is. And what that means is that the 5 warmest years out of the last 170 are all in the last 5 years. I mean, that's remarkable, and it's not a pattern. I think there's one other place in this time series where you could say the same thing just once. I mean, it's one of those indicators of, yeah, this really is kind of weird. A lot of that heat has gone into the ocean. This is not going back nearly as far. It's to 1960. And this is heat content estimated for the oceans. And these are big numbers. They're petajoules, which is 10 to the 22nd, if you remember what a joule is from your high school physics class. It's a lot of heat. And so we've noticed since, the baseline period, they usually set around 1980, but we've noticed since this little plateau here that we've accumulated 25 excess petajoules of heat. And that's the heat of global warming. It's heat going from the atmosphere into the sea. And so we think it's at least 94%. And I met with Jim Hansen a couple of days ago in Washington, and he says, honestly, it could be 98%. So the ocean is bailing us out from having a much worse problem on land, right? The ocean is air conditioning all of our terrestrial spaces. But that means that if we were to figure out a way to remove CO2 immediately, then the ocean would start giving heat back out. It's a big flywheel, and it means at some point, as Susan Solomon has written, that climate change becomes irreversible for 500 years because of heat storage in the ocean. And so it behooves us to understand this, to measure the heat uptake in the ocean. The impacts of climate change are very heterogeneous. This is 1 month of climate anomalies. It's last month, October, right? And it's broken down into these, 5 degree or 3 by 3 degree boxes here. And the way it works is anything that's in the pink or red color is warmer than average, much warmer, or record warmth ever, right? And white is neutral, neither warmer nor colder. Blue is a little bit colder. So last month, there was a single grid point on the globe where a record cold was set, probably here around Wyoming. And that's why, that's where Dick Cheney comes from. And Dick Cheney doesn't believe in global warming. Well, maybe it never happens there. But, there's 2 parts of Mexico that set, you had extremely hot weather here in August, right? Very hot, 3 degrees above the climatology in many parts of the country. But even in October, you're still setting record warmth. If you add up these, there's about 55 record warm grid points and only 1 record low. And so, you look at these temperature changes, 1 degree centigrade, it doesn't seem like it's so much, but the problem is it's heterogeneously distributed. In some of these cases in southwestern Africa, they're 4 to 5 degrees centigrade above the average. And that's what does the real damage, right? So it's, nobody lives globally, we live locally, and the expression of global warming is much more extreme at the local level. So this came out a couple of days ago in Scientific American, October, our second warmest October on record. I read this piece about record-breaking August temperatures in Mexico, so that's becoming well known. And there was a heat wave that killed quite a few people in Japan in 2018, and a lot of Japanese climate scientists have been working on explaining that. And because of the way the physics work for Japan in that particular hot time, this was the headline. That would not have happened without the 1 degree of global warming that's occurred already. And I suspect that attribution of intense heat waves to just 2 man-made effects can be made for many other heat waves. So this is a problem for all of us. I think it's a big problem for Mexico. Some places are more susceptible, but most years, heat waves are the single largest cause of human death related to climate. And I was at a climate change meeting in Norway at this time in 2003. That's when 70,000 people died, half of them in France, older people at homes in France, but from a heat wave, because nobody had the concept that it could be that bad, that hot, that long. Same thing in Russia, and in the US, it's 700 people about every year.
And these are official figures.
Yes, this comes from the World Health Organization. They're probably smaller numbers in some cases, like in Africa. Well, they don't even show the numbers for Africa. I don't think they have a good, and they have to separate heat waves from malnutrition. And there's so much malnutrition in that areas where people are migrating. So, to me, I worry a lot about heat waves, and I worry about the heat waves not just 50 years from now, but next year, the year after that. And we're not really slowing things down right now. The the orange line here is the Hadley temperature record, and then these colored lines are different representative concentration pathways. The most aggressive consumption of fuel puts us at RCP 8.5, and that's the one we've generally been on. We haven't seen a significant reduction away, and that one, by the year 2050, takes us up to 2 degrees. So many of you in the room, you're going to be in your prime right then dealing with this very, very changed planet, and it's not that far ahead, right? So that part of the news isn't very good. I've got to load up this other one because you'll see why I did it in a second. I removed one slide for the version that's going to be uploaded as a file for you guys, and it's this one. And the reason is, let's see, how do we get that screen to go away? Well, I think we have to do this. We'll just go through it fast. Okay, so right now I'm serving on a board of the U.S. National Academy of Sciences, and it's the board on atmospheric science and climate. And we advise the president. The president doesn't want any advice, and I've never met him. I certainly didn't vote for him. I have given money to impeach him. But last Friday, I did meet with the president's science advisor, and a guy named Kelvin Drogmeyer, and one of the topics was, when are we going to get going with climate? And he says, well, this president just isn't going to do anything. So he comes out with, just crazy things. He's done tremendous damage to our Department of Energy, our Environmental Protection Agency, rules and regulations and rollbacks. He's allowing massive scale logging in the world's largest temperate rainforest, the Tongass. And it can't go on. But I've seen a level of activism like I never could have imagined. So I think it's going to change and change pretty fast. I think he'll get impeached by the House, acquitted by the Senate, and that the Senate will then transition to a Democratic majority. Now, we could talk about this all day, but we can't. We've got to talk about science and sustainability. Okay, so what we really know, these are 7 different studies. I know 4 of those authors quite well who've done different techniques to review the literature. They've examined over 55,000 peer-reviewed scientific articles. And then these numbers are the percentages at which scientists agree that humans cause global warming, right? It's not surprising. There's always going to be some deniers, or maybe somebody only works in Wyoming in that one cold spot. Okay, so let's go into the ocean now. So Mexico's coastal waters continue to be anomalously warm. If you look at the seas on both sides, Gulf of Mexico, Caribbean Sea, also off of the Pacific coast, the seas here are warming about 50% higher than the rest of the ocean. And this time series, these are weekly average temperatures starting in September, ending in November, about a week ago. And so you can see the reds here, and the anomalies are, on that order of 1 to 1.5 degrees C. So that's already stressing communities there, and it puts stress on corals. We think about coral bleaching, but it can put stress on mangrove systems as well. It causes the ocean to be a little bit higher when storms come in because the ocean's warm. And so that's one question, I think, is trying to figure out, what do marine heat waves do to Mexico's coastal ecosystems? Like if I were wanting to safeguard the coastline here, I would launch a research program on that topic. On a global scale, these marine heat waves, we've had 3 really big heat waves. This one just happened to occur March, April, May, 2015, 2016, and at that time I was doing field work in this part of the Indian Ocean. We'll go there later too, but this induced the third global mass bleaching event, and in many ways the worst. At this time, something like 60% of the corals bleached overall, and the majority of those died. Some of them came back. If they're stressed to the point where they expel their symbiotic algae and then the stress goes away, they can recover, but normally they don't. And if the heating is maintained for more than 2 or 3 months, 90% mortality, something like that. So it was the third global mass bleaching event. The first one occurred in 1982-83. The second one in the late 90s, early 2000s. And the thing is, those are pretty close together in time. Some of these corals here are 50 years old. So, you're knocking them down before they get a chance to develop into a climax assemblage of reef organisms. So Mexico has quite a few reefs. This is from Reef Base, and you've got reefs. The beginning of the Mesoamerican reef tract is up here, and then Belize, but you've got reefs around the corner into the Gulf, both sides of central Mexico and on up into Baja California, and also on some of the islands offshore. And so that is something you're going to want to safeguard for reasons that I'll talk about in a second. Okay, then there's, talk about it now. Here's projections of how often bleaching is likely to occur in different parts of the ocean based on a simple ocean model of future warming. And so here we are in the 2030s, right? That's going to start in 11 years, and you can see Baja California doesn't look too bad. Parts of the Gulf don't look too bad. Even the Big Barrier Reef doesn't look too bad. It takes us down to maybe half of the years there'll be some kind of bleaching alert. But by the time you move ahead into the 2050s, the ocean's warmed up past kind of a bleaching threshold for many species, and then it's like every year there's potential for bleaching. Now, this is kind of simple-minded because they're living organisms. They adapt, right? There's Mendelian selection, Darwinian selection that occurs. In some cases, we can help that. We know that. We can stress corals and have stressed corals breed with other stressed corals, and you create supercorals. That's being done right now. I don't know of it being done in Mexico, but it always works best if you do it locally on the reefs that you're trying to save. Like we have thermally resilient corals in the Republic of Palau. We could bring them here. There'd be all kinds of permitting issues, but it's not clear they would do well. So those kinds of experiments should be done here to protect your corals. Okay, then that thing I said, it's in the title, tropical coast. If you think about it, tropical coasts are really important. It's 1.5 billion people live within 100 kilometers of the coast. And these numbers are rising quite a bit. So that's about 21% of the total population, and it lives on 7% of the land area. So it's densely inhabited, and it has a number of problems. So some of them are health challenges, as because of the high human and animal populations, low gradient coastlines, climate change. We've seen major dislocations or translocations of where diseases occur. The rise in dengue can be attributed to climate change in many areas. Zika, malaria, I mean, there's all kinds of things that are directly related to climate change. So there's a variety of stressors that degrade these coastal environments. They have to be maintained as healthy environments. They provide food, protein, and that sort of thing. Sea level, I think, is going to be a much bigger deal this century than people have been talking about. I think IPCC grossly underestimates the possible magnitude of sea level rise, and I say that because of the work of many of us in Antarctica, where we directly measure melt rates of Antarctic ice and now Greenland ice, and it's melting faster, much faster. Okay, so you're going to deal with bigger and stronger storms. This is Hurricane Harvey And I used to live in Houston, Texas, so I still have a lot of friends and family there. But, you know, this storm, what a beautiful feature of the atmosphere, right? It's such a tight eye, but it came on shore and it just stalled out, and it rained over a meter in about 40 hours. 1 meter. And it did that for a number of reasons. It's a really big storm, but you know what? The Gulf of Mexico and the atmosphere there was 2 degrees warmer than normal. And for every degree of warming, the atmosphere holds 7% more water vapor. So the wet atmosphere that was fueling this storm started with 14% more fuel. You know, that is really simple physics. And so, you know, with this talk about attribution of more storms, bigger storms, where they're going to hit, that can be a little bit tricky, but the simple physics dictates that when the storms happen, they're going to carry more water. And when they carry more water, they're going to create more rain, and there'll be more coastal flooding. Mexico already gets a lot of storms in both the Caribbean realm and then in the Eastern Pacific. Of course, this is because of that huge area of hot water. You know, we get the strongest, biggest typhoons and cyclones in the Western Pacific. And, you know, just that observation alone tells us that if the Atlantic warms up so that this becomes a warm pool of water similar to what was here 50 years ago, then we'll get bigger storms here. You know, it's a straightforward, logical argument. But some experiments have been done on this. This was done by Alexei Fedorov and published in Nature almost 10 years ago now, where he set up a climate system like today. This is 1 year of climate, and these are tropical storm tracks. And when they get yellow, orange, and red, they're like big hurricanes or typhoons or cyclones. And then he ran the same experiment again using kind of a baseline temperature of the planet of the Pliocene. We know a lot about the Pliocene. Geologists have been working on it for a long time. And planetary temperatures were about 3 degrees warmer than they were, than they are today. And if you warm the ocean up the way we think it was warmed up at that time, then all of a sudden, for the first time ever, you get large tropical storms and hurricanes in the South Atlantic. You know, normally that's an area that's just devoid. Imagine living in a small coastal town in Brazil and you see a hurricane. It's a place that hasn't had a hurricane for 10,000 years. Many more and much stronger storms here. And then there is an increase in the intensity of hurricanes in the Caribbean realm and also in the Eastern Pacific. It almost looks like they've moved away from the coast. I don't know if that's a real phenomena, but I'd say there's a pretty good argument that storms will become stronger, more frequent, and because of where Mexico sits, you're going to get hit on both sides. So when those storms come in, they'll be working with water that's occupying a higher level in the basins, and maybe this tiny little anomaly here that allows big storm waves that when they come in at high tide, then water being pushed by the wind can raise tides another 3 to 5 meters in some cases, that's going to become much more common. And very few of our coastlines are hardened against that kind of a process, right? So that's another area where I'm sure people in Mexico are thinking about this. What do we do to protect our ag coastlines and our urban coastlines where they cost so much? I mean, things like this happen. This is in North Carolina. Like in the US, it's considered that 25% of homes and other structures are going to be victims of erosion from storm surges within the next 50 years, right? So people that buy these things, they can no longer get insurance. And it does terrible things to infrastructure. So this would apply to many parts of the Gulf as well. One of the things I work on is when we have more coastal flooding, much higher rainfall during big tropical storm events, then a lot more sediment gets washed out into the ocean. This actually is not a bad thing for mangrove coastlines, but it's death to coral reefs. And So, this is something coral reefs are going to have a very difficult time adapting to increased sediment loading that's caused by stronger storms. I mean, the main thing you can do on land is put in sediment traps. You can revert to sustainable land use chain practices that tend not to leave erodible muds and silts at the surface. But that's not what we're doing now, if you go see how developers develop. And you should care about your coral reefs. You've got some great ones here. Biodiversity, it's the Amazon rainforest of the sea. 12% of the world's fish catches on coral reefs, so it's super important. Protein for tropical populations. It's essential in Indonesia. I mean, that's it. At least a third of the Indonesian population only has access to protein from the sea. They protect islands from storms, tourism, obviously. Mexico's tapped into that in a pretty big way. They have cultural value for indigenous communities and so forth and so on. So now we're going into part 2 of the talk. Let me check my timing here. I think we'll be okay. I'm going to show you how we use samples from corals to say how climate changes naturally and how we attribute unnatural change, right, to man's activities. And you guys are doing some of this in the Marine Science Institute. You have a coral drill and you've got some students under good guidance that are trying to understand climate change. And so, I used to show this figure all the time. It is the hockey stick. One of the people that contributed this to IPCC AR3. I showed this stuff at the Copenhagen Convention on Climate Change, and the Republicans in the US called it the hockey stick. But it's 1,000 years of temperature reconstructed from paleo archives, things like tree rings, coral cores, sediment cores, ice cores. It's all in here. And then as you move forward through time, you can see that over the last 1,000 years, it's mostly been cooling a little bit. And then all of a sudden around 1900, it takes off. And so this is the blade of the hockey stick, and that's the shaft that you hold on to. And so this light gray is kind of an air envelope, and the air envelope contracts around 1600. That's mainly because most of the corals come in there. The corals are near instrumental thermometers, and as long as the coral's growing day in, day out, it's measuring the temperature of the sea. It's also measuring any insults that might happen. If there's a mine tailing spill and it doesn't kill the coral, then the coral is going to incorporate the evidence of heavy metal, an increase in heavy metals in the coastal waters. It records if you're putting on too much furniture in the Yaqui Valley near Guaymas, which they do. So much nitrogen, so heavily subsidized by the government. You can see that nitrogen that washes off of the ag fields goes into the sea, and any carbonate organism that's building a shell shows like, oh, a bunch of nitrogen here now. So you can use it in a forensic sense, right? Crime scene investigation on the coral reef. So partly what we're doing here and what I'll talk about now is how do we know what's natural? And I mean, in this case, here's natural, like these little excursions of 0.2, 0.3, 0.4 degrees centigrade, century scale, but we don't see anything like this. And we've been able to reconstruct this going back almost 10,000 years now. So now I'm going to take you to the site where we drilled a coral named Big Mama. And Big Mama lives here. Big Mama's still alive. There's this figure is a correlation of the index of El Nino in 3.4 region against temperature in the ocean. So it's a time series regressed onto a spatial array of data. And so this is the homeland, the heartland of El Nino. When you have an El Nino, it's really hot here, it's a little bit colder here, a little bit colder here. And so Big Mama is right on the boundary where the gradient is steepest in water temperature between El Nino and La Nina. So we thought, let's go there, drill there, and we can see if the footprint of El Nino expands or contracts. And it's also the site of the largest known coral colony on Earth. This is Big Mama. Big Mama is 22 meters in diameter and 12 meters high. And she's been alive for over 1,000 years. And that's a question in itself. This huge coral lives in a valley underwater. They call the Valley of the Giants because they're all big. Why? You know, why there? You don't see anything like that on the Great Barrier Reef or in the Mesoamerican Reef Tract. There's nothing that big. The tribes people that live there, they call this thing the tumor, but it's not. I mean, it's just a different growth form on the coral. They said, does it have cancer? I said, I don't know. It looks healthy to me. So this is a national park, but there's no hotels, there's no restaurants, there's no transport. You can only go there by making friends with the tribes people that live there. And it took me 5 years to convince them that they should let me drill Big Mama. It's fairly violent. You know, so they were worried this would kill the coral, but the coral's still there. It's perfectly fine. So what happens is we come back with maybe 300 kilograms of coral core. That's 20 meters of core. We've triple cored it as far as we could go with our drill system, and then other cores just over different parts of the dome. And that's how we do our replication studies. We bring them back to the lab and X-ray them, and in this case, this coral, you can count these annual growth bands, and they go back to 1479. We think we can go there and go back maybe to the year 1100 on a future trip, but we have to finish publishing what we have now. So what do we do with those corals? There's a bunch of things that you can do. These are the annual growth bands produced as the coral diverts metabolic energy from feeding into reproduction, things like that. And so you can count those bands. There's even lunar monthly bands, right? In clear water areas, when the moon is full, the zooplankton don't come up as high onto the reef, and so the coral's starving a bit, and it makes a dense layer in its skeleton. And then in a new moon, when it's really dark, there's tons of food, and the coral grows really fast. So, you know, that you can, in a coral like this, you can do monthly scale timing, right? Like here's, you know, April 1872. It's difficult in most corals. So it's grown about 1.5 to 2 centimeters a year. It's made of aragonite. We can see fish bites, right? So these are parrotfish bites, fish grazing scars. And one of the things we've noticed is that the radius of the bites gets smaller. You know, like you look at corals 300 years ago, and the bite radius is like that. And now they're like that. That's because all the big ones were fished, right? The fishermen are excellent fishermen, and they fish the big fish first. So I'm going to show you some isotopic data, delta O18, and the functional relationship here is that if this coral is growing in warmer water, delta O18 drops. Likewise, there's a salinity signal here. As the salinity rises, this indicator, this tracer, delta O18 goes up. And so that's how we interpret these things. And here's a 500-year record, the longest coral record that's yet been produced and published. And the temperature rise here since the 1500s is at least 1.5 degrees. Since 1900 or so, around about there, you know, it's actually a little bit less than the global average, but that's partly due to the heterogeneous response of global warming. This is a really interesting feature here in the late 1700s. It's prior to the main part of the Industrial Revolution. So this is a large step up in temperatures that occurred by natural processes, and we've got a modeling group working on that now. All these ups and downs mostly reflect there are El Niños. There's a very, very strong El Niño signal here. As El Niños, that pattern expands and contracts, it shows up as temperatures at this site. So we published this paper late last year on El Niño's shrinking 20th century footprint. And so we think that's one of the manifestations of climate change in this part of the Pacific, is that El Niños happen, but the part of the ocean that gets really hot becomes smaller, right? That makes more intense heating in places like Galapagos, so they should expect to see a lot more coral bleaching. And that's, we don't fully understand the physics of that yet, but it's one manifestation of climate change. And so this is one of the figures from that paper, and I don't want to spend as much time as we could on this, but it's the standard deviation of the isotopic signal in this 2 to 7 year band, which is where El Nino manifests. And the black one's the one we're going to look at, is from American Samoa, from Tau. And when it's up high like this, that means that there's very large ENSO variance. And when it drops to really low values, it's ENSO is idling, or it's hardly present at all, that they're very weak El Niños, weak La Niñas, right? And so we're actually heading into a phase of weaker and weaker El Niños and La Niñas here towards the end of the 20th century. So that's one way we use that kind of data. I have got one other quick example before we go into the last part of the talk, and that's on megadroughts. So I've done a little bit of work on megadroughts. We actually haven't had a real megadrought since the late 1800s. The last one in India happened like 1887 to 1892, 83, but at that time, in a very short period, 4 million people died from crop failures related to this drought. So these are profound droughts that last multiple years, in some cases decades. And the droughts of East Africa, they last decades, right? So this is a core that we collected from offshore the Sabaki-Galana River. These are the rivers that drain some of the most heavily populated parts of Kenya. Lake Naivasha is up here, where all the penguins are. This is the wine-growing district of Kenya. And in 2000, a guy named Dirk Verschuren took a sediment core from a lake, and going back through time, it's 900 AD up to 2000, he reconstructed the level of water in the lake. And the lake's a closed basin lake, but it dries up. So here's the time here, this particular drought, 1755 to 1820, the lake is basically a salt puddle. But before that, it was overflowing, at least 40 meters deep. And then it dried up again here, it dried up again here, and then a long period of dry lake. And if you look at local, cultural, and oral history, these droughts are all named. People knew what they were. They knew they were very damaging. And between the droughts are these ages of prosperity where people prospered. And then you have the droughts where in some cases 90% of the population passed away. They couldn't grow food. So we were asking the question, what causes these droughts? And from a coral record from Kenya, the answer is pretty simple. It's cold water. So this is sub-weekly scale isotopes going back to the year 1700, right near the mouth of that river. And so we're tracking temperature of the coastal water column close to where that river comes out. And here's global warming at the end. The last few years, the last decade here, exceeds the envelope of warmth anywhere else in the preceding time series. And then there's this funny period, 1755 to 1820, where we see these excursions to really low values. That's our temperature calibration. So this would take us down 4 degrees below the average, and on the order of 2 to 3 degrees colder for 70 years. Now that's really important. There's this thing called the convective limit in tropical meteorology. Once temperature drops below about 28 degrees, it's really hard to create deep convection with moisture coming from the ocean extending up high into the atmosphere. This would have been a time when there would be no snows on Mount Kilimanjaro because the ocean was too cold to provide the energy to uplift water to the top of the mountain. So the proximal cause here is cold water. We don't know. This is right on the equator. and the water got so cold that it wasn't supporting rainfall. And we don't know what caused that. We don't know if it could happen again in some places, but the prospect of mega droughts, like India, for example, is not prepared to deal with a mega drought. They weren't prepared in 1888, and they're much less so now. Okay, last part of the talk, be pretty quick, relates to the carbonate production factories that exist on coral reefs. They're the biggest cement factories on Earth, right? There's a lot of cement produced here in Mexico to build my hotel and the buildings here on campus, But if you said, how does the volume of cement production worldwide compare to what coral reefs do when they're healthy? It's actually a pretty small number. These are the biggest cement factories on Earth. They can accumulate coral carbonate skeleton very quickly. Some species can grow 8 centimeters in a year, and they occupy large areas. So, they're super important. This island is Nelson's Island in Chagos. It is a very birdy island. There's about 2 million birds on that island, and that's the case because the island is rat-free. The British removed all the rats about 50 years ago, and that island has birds. And because there's so many birds there, they're bringing back nutrients that wash out into the coastal ocean and fuel productivity. And this reef is growing almost twice as fast as any of the adjacent reefs on islands that don't have birds. And you can see what it's done, right? Like the reef is prograded way out in this direction where storm waves are coming in, and it protects the coastline of this flat island from wave erosion. It's also true, sea level could rise 2 meters in the next 100 years. That island's probably going to make it. It's building enough new cement that it can lift itself up out of the sea by 2 meters, right? And that's true for coastlines as well, not just islands like this. And so the thing that, that goes with global warming is ocean acidification. Sometimes it's called global warming's evil twin. It's a very different kind of physics. It's the uptake of carbon dioxide from fossil fuels by the ocean. And it's already made a significant change in ocean pH. In 1850, the global ocean pH at the surface averaged 8.2. Now it's just under 8.1. And if we look ahead to the year 2100, we expect it to be down to 7.7. Now this is a logarithmic scale, so it's a big change in hydrogen ion activity. This is pretty easy to predict, right? I mean, there's nothing complicated here. You can't argue against this process and what it does. I mean, people do argue, and I talked to a lot of senators and staffers and representatives in Washington, D.C., and the general response is from people like Ted Cruz, well, yeah, no, I get it. I mean, that science seems pretty simple, and I'm not stupid. You're probably right, but my voters aren't going to like it if I talk about climate change being real. That's what we're up against. Okay, so we are starting to look at what happens. My lab specializes in trying to find things in the lab that we can take into the reef. This is a free ocean CO2 enrichment experiment, something that I did with Davy Klein, where we had it out for 6 months, and we're injecting water of the future, low CO2 or high CO2 water upstream, and then we look at how things grow in that flume. Davy just moved from San Diego to Panama and has got a really nice setup at Boca del Toro. He'd be a great partner for you guys too. Let's see. Okay, the last little bit here is stuff that we've just started. This is the British Indian Ocean Territory. Right here, Diego Garcia is an American base. And we're asking a number of questions. What's the full biodiversity on reefs? That's never really been figured out. Like, we go there and we see the fish and the corals. The big things are easy for us to see, but there's a huge cryptic community, tiny things, decapods, bacterial communities that are super important for the functioning. So we do not yet have a model for the essential guilds of organisms that have to be present for a reef to be healthy. We don't have that for any reef on Earth. So we're trying to figure out the full biodiversity. Of course, that gets done now with genomic techniques. We've also asked some questions about natural variability and what does that mean for resilience and how might you use that knowledge to create protected areas. And then this is a place where we can ask the question, are pristine reefs more resilient to warming and acidification? Because, I mean, it was a bad thing that the UK did in 1969. The United Kingdom went to these islands and they removed every person that was living there against their will, 3,000 people, 1969, and they moved them to Mauritius and some of them to London. And then they let the US build a gigantic airbase. And so nobody lives here, there's no pollution, there's no sewage. There's a little bit of fishing, but you know, you gotta be pretty brave because there's all these fighter jets flying around, right? So it really is unimpacted. And it's good for science, it's bad for the Jacosian people. So anyway, these are my partners from Oxford. These are young genomicists that have learned all the techniques to do species identifications. And we put out these things called ARMs. They're autonomous reef monitoring structures. They're just condominiums. You put them out for, you know, these are out for 5 years, but we get some back every year. And things grow on them. We identify that. We put some of it in a blender, blend it up, and do genetic description. So far, I think we've discovered over 200 species of kind of crustaceans that nobody knew were an important part of the reef, maybe 40 species of sponges. And so that's all being done with these different genomic techniques that I'm sure UNAM has become involved with, and almost certainly the Marine Institute as well. Super powerful, it's become so much cheaper now, and it's especially good for young people in science to learn these things. Okay, so yeah, human free since 1972. Those bad Brits. I have to be careful when I go there because I can only go there with the British. You can only go on a British ship. Okay, so I'm coming very quickly to the end. I wanted to show you a couple of things, but we've put out all kinds of instruments there. We're trying to figure out, you know, is the physics the same everywhere? So there's current meters, there's temperature loggers, there's salinity recorders, things that let you study physical properties. And here's one example from 2016. We've got almost 4 years of data now, but this is a blow up from July 13th to July 18th, so just 5 days. And it's temperature. Temperature recorded every 15 seconds. And you can see these solid kind of gold, purple, red lines. They're all around 28 degrees centigrade. But then there are some other sites where temperatures will drop down, you know, to 21 degrees for 2 hours and then pop back up again, right? So these are high thermal variability sites. And we think those are internal waves that are coming in and hitting the pedestal. So when it's stormy in the Southern Ocean, Antarctica, these big surface waves are also accompanied by internal waves, and these internal waves propagate along the thermocline for thousands of kilometers, and they hit these islands. And if it's a site that's exposed to that, all this cold water gets driven up. So why is that important? Well, the idea is that these corals adapt to their thermal environment. So those corals that live in those high thermal variability environments, you know, they already have a genetic makeup that makes them adaptive to thermal variability, maybe even to higher temperatures. So we measure the genomic properties of the resilient and the non-resilient corals. We've done some transplants, and the warm water only corals, you know, they only last a week. They're dead. They can't handle those cold temperatures. And now we're trying the other experiment to see if the highly variable environment corals can live in a hot place. Okay, then we're also making these real-time measurements of the carbonate system, which would be a fun thing to do with one of your lab operations in Puerto Morales in the Caribbean. And this is how it looks. So it's kind of a mess. I mean, we called it super beams because there's like 12 instruments here, and there's strong waves and currents, but this is a pretty cool system where we use boundary layer physics to very precisely measure the pulse of the reef, like net production of food, net respiration, net calcification, net dissolution of carbonate. And so it works like this. There's pumping system that moves water around. There's a CFET pH sensor. There's a very accurate system that measures temperature, salinity, and dissolved oxygen. Super expensive Norwegian current meter. Light logger, another pH logger. And the pump is pumping water from 20 centimeters above the reef and also from 70 centimeters above the reef. So we're looking for boundary layer gradients. And we always find them. We also look for the physics to be right. This is current speed in centimeters per second as a function of height above the bottom. It's every centimeter. So we're from 20 centimeters all the way up to 120 or so. And this is a nice benthic boundary layer profile. That one is very easily described by kind of classical drag physics. And when it looks like that, then we can employ some pretty straightforward equations to calculate fluxes, right? So we put all this together with the chemical measurements, and just as an example of what some of these data sets look like, here's a week in the life of one of these reefs, and the shaded areas, that's nighttime, daytime, nighttime, daytime, nighttime, and let's just look at oxygen, right? Oxygen is high in the daytime, that's good. Means it's photosynthetic. Oxygen drops at night because there's respiration, it goes up again, goes down. Well, we keep track of, here it didn't go down as far. There's sometimes it doesn't go up as far. And we can generally associate that with light intensity. Light is just super important. So that's the diurnal variability, and we can make some pretty key calculations with that. But the real information comes from these pump switches. And so in this case, every 20 minutes, we're pumping from 70 centimeters. Actually, I guess in this case, it's 58 centimeters and then 116 centimeters. So these two need to be reversed. But upper pump, lower pump, upper pump, lower pump, upper pump. And then this is a pH logger that's receiving that same water, and it's recording pH every 3 seconds. And so we developed these plateaus. And there are small differences. Like between that one and that one, it's only 0.004 pH units, right? I mean, that's a really small number, but we only care about relative differences. And it repeats itself over and over. So, in this case, where the pH is lower, right, on the pump that's on the sample being taken from near the sea floor, it tells you that that community is calcifying because that produces CO2 and lower pH, right? And so the physics allows us to calculate exactly what that flux is. So we can measure hour to hour, day and night, how much food's being produced, how much respiration's being produced, how much calcification is occurring, how much carbonate is dissolving. So you can tell pretty quickly, is this part of the reef going to be around in a year or two, or is it dissolving away? And so, these are pretty complicated chemical and physical arguments, but I'm going to summarize that here. So what did we learn? Well, we observed net community production, primary production that was producing 130 millimoles of oxygen per meter squared per day, and at night when it was respiring, it's about minus 110. Net community calcification was as high as 150 millimoles of calcium carbonate being formed every day, every square meter. On an hourly basis, those numbers are good to about 10%. And light intensity is extremely important. We see when a cloud comes across the sun, the rate of carbonate production could drop by 80% and stay there for 20 minutes until the sun comes back out. It's that sensitive. That's why sedimentation that intercepts light in the water column. It's one of the reasons that's such a bad thing. And in this case, pristine reefs, the community was net producing carbonate as well as food available for export. And we think it was a lot of food. Like here, we would argue that all the sharks and tuna, the big pelagic predators, they're in abundance offshore because of food subsidies coming from this island system. And that's something worth knowing. Okay, I've only got 2 more slides. I wanted to point out, I showed you all those instruments on the bottom. I mean, it's a mess. It costs a lot of money. We're trying to figure out how to keep them out there for a year. But you can actually learn something just by going out every now and then in a small boat, taking some water samples and bringing them back to the lab and measuring 2 things. Measuring dissolved inorganic carbon, or total CO2, and alkalinity, these 2 parameters. And the reason those are important is if you have those 2, then you immediately know the relative ratios of photosynthetic respiration processes versus calcification and dissolution. And those of us that have been doing this kind of work for 20 years now, we've just got this sense, you go to really healthy reefs and water samples are going to plot up in a certain angle. It's kind of more like the red numbers here are a healthy reef system. And if you're up here or going like that, it's not, right? So if you have a reef that's converting over to algal dominance, macroalgal dominance, then you're going to start seeing your water samples lying more like that as calcification becomes less important. So, that's something anybody can do. You can go out and get water samples. You don't have to have a bunch of fancy instruments deployed on the bottom. And there's a number of papers out there that describe how this can be done. And we have a little workshop tomorrow where we're going to work through some of these calculations. So this is the last slide. And I'm sure I've gone a little bit too long here. It's 5 after. I'm so sorry. So, we think about this a lot. Like I have kids, a lot of you guys have kids. My boys love coral reefs. I got them out diving when they were 12. And I want them and their kids to see things like this. And it's not clear they're going to be able to. What do you do? I mean, the global cause are the global emissions of CO2 from fossil fuels, from cement production, from deforestation. And that's like number 1. It has to be addressed. We don't have an effective way to do it in the international arena. But that has to be solved. But in every case related to coral reef, local management of the local stressors. So the local stressors are overfishing, sedimentation, sewage, land use change, all of that stuff gets in there. And I'd say one of the things we've learned is that reefs that are not subject to the local stressors are much more resilient to warming and acidification, right? So I think we have enough scientific facts about that now. You can just take that to the managers and use that as a framework for designating more marine protected areas. Mangroves, especially for Mexico, there was that, it's not so big now, but remember when all those shrimp were being grown and these developers would come in and make a shrimp tank in a mangrove forest and then move to the next area. This was extremely bad for coastal protection. And on some of the low gradient coastlines, you really need those mangroves to protect storm surges, to keep the storm surges from going into agricultural systems inland. Once you salinify, if you have a big storm surge that brings salt water 10 kilometers inland on a productive field, it takes a long time to get the salt back out. And until the salt is gone, the crops aren't going to grow. So it's protecting those coasts. It's kind of paramount. And I hope that it's a big part of your sustainability initiative. So I will stop there. Thank you very much. Namaste.
Thank you very much, Rob. I think we should all be... perdón, cambio español. Conozco a Rob desde hace bastante tiempo, es un buen amigo y la verdad es que cada vez que lo oigo hablar, pues siempre hay algo que me sorprende y siempre hay algo que me emociona de lo que dice, ¿no? Rob entiende bastante bien el español, pero como decía antes, no lo habla. Vamos a tener más tarde una mesa redonda donde vamos a tener la participación de otras personas y seguiremos discutiendo, pero creo que es bueno que aprovechemos este momento pues, para hablar con él 5 o 10 minutos, aunque retrasemos un poquito la presentación, etc. Entonces, si alguno de vosotros, de ustedes, no os veis con ánimo de hacer la pregunta en inglés, la hacéis en español y yo apoyo a Rob para traducir. Yo tengo muchísimas preguntas que hacer, pero no lo voy a hacer. Creo que es vuestro momento de hacerlo. No sé si a través de Facebook hay abierta una sesión de preguntas también. No sé si... Está transmitiendo. Bueno. Me parece muy bien. Pues dicho lo cual, I open the floor for questions. Alfonso.
I'm trying to speak in English. What about you mentioned the drought in Africa for a long time, for many years. But I was very surprised at that. In fact, yesterday in the news, Africa, especially Kenya, Somalia, Tanzania, were under what?
Yes.
Heavy rain, and 1 more million people still in that problem. Would you mention something about it?
Yeah. So one of the more certain predictions from the whole suite of IPCC models, or systems models now, for the future is greater variability in the hydrological cycle. So it means more dramatic rainfall events during rainy periods, stronger, wetter storms. But it also means that when droughts occur, that the droughts are stronger and longer. And so you put those two things together in places like the Kenyan highlands or the Ethiopian highlands, which are already pretty dry. You know, if they have an extended drought period, maybe some fires, and the fires in the brushlands crystallize minerals, organic phases in the soil. And then it's followed by a big rainfall event, then that's when everything moves. Rapid erosion of the landscape. And that's been going on for a long time in Kenya. My group's done some work on the long-term history of land use change, and it demonstrates how simple things can just go so wrong. When the British, everybody in Europe was colonizing some part of Africa, and the British were there in Kenya and the Germans were in Tanganyika, and one of their thoughts that occurred around 1900 was, well, let's try to grow coffee. And so they clear-cut the coastal plains of Kenya and tried to grow coffee. And it turned out coffee didn't grow very well there. The coffee wanted to be up on the slopes of the mountains like Kenya and Kilimanjaro. Well, so they stopped, and then after that, this is a landscape out of equilibrium that just started dumping sediments. Every time it rained, sediments that had been stabilized went into the rivers and carried it to the sea. And we measure that sediment in those corals. I didn't show you the data, but you can see all of a sudden, when the coffee plantations failed, the sediment loading in the coral skeletons jumps way up. And it's still high today. In 100 years, the landscape hasn't achieved equilibrium. So, the combination of man's activities in agricultural ways, sometimes just road construction, with this increased variance in the hydrological cycle, it's just a recipe for disaster. Mobilization of sediments, loss of topsoils, all of those. These mega droughts, I worked for a number of years in Bolivia in Lake Titicaca, and we discovered that about 5,000 years ago, Lake Titicaca dropped almost 100 meters, and lost 2/3 of its volume. And it only took it about 50 years to drop, right? So imagine, you're living there, growing oyukos, these potatoes, and every year the lake is 2 meters lower, right? So people had to move. It was a big disaster. The lake ended up becoming really too salty to support potato culture. Lasted for several centuries and then filled back up again. And so that's a natural part of the climate system. We don't know what caused it, but it tells us there's thresholds and surprises that can kick in. But good question.
Okay.
¿Alguna pregunta más? What happened in the 70s, Rob, that this warming starts and has not stopped?
Yeah, well, I graduated from high school. But
So you are.
I had a good time in the 70s. Let's see. So the oceans can either absorb a lot of heat or a little heat, depending on whether it's an El Nino, La Nina. We have a lot of oscillators in the ocean that operate at decadal timescales, like the Pacific decadal oscillation, the Atlantic oscillation. And so the way we've simulated these changes in slope of the atmospheric warming trend most successfully always involves changing oceanic uptake of heat. So in the 70s, where it kind of flatlines for a while, that would have been a time when more heat was going into the Southern Ocean and a little bit more heat in the North Atlantic as well, and it kept the atmosphere from getting warmer. 5 years ago, people would give talks like that at AGU, and they'd be challenged, but I think now everybody accepts it. It's the ups and downs. There was a U.S. Republican talking point for a long time claiming that global warming stopped in 1998, because that was a big El Nino, it was a big hot spike, but we've since acquired data on warming in the ocean, and it accelerates every year through that period. It never stopped, and since most of the heat goes into the ocean, that's where the signal is. It's not in the atmosphere. I mean, we keep showing all these figures of temperatures amalgamated from land, but the heat of global warming goes into the ocean. That's where we should be focusing our best studies. So.
Nadie se atreve, ni que sea en castellano, yo traduzco. Es vuestra última oportunidad. Ok.
No worries.
Sí, una pregunta de Facebook.
Okay. What should Mexico be doing to reduce the global warming problem? And especially considering the difference between the Pacific, the Caribbean, the Gulf of California, and the Gulf of Mexico. That's a question by Armando Avila.
And answered in one sentence. Now, I teach at a university. I love teaching at a university. I am the faculty representative of fossil-free Stanford. So we have 150 students that are active in causing the university to divest of fossil fuels. And last year, they took over the president's office, right? So I didn't do that, but I did bring them some food. And so actually, I think there's a lot to be said for those kinds of actions, but I also know that until we have alternatives, we're not going to move away from fossil fuels. And so to me, the best thing is to well, I don't know the extent of the Mexican government's investment in renewable technologies, but in the two states where there's been a lot of government investment in the U.S., it's been tremendous. Texas, despite having a bunch of crazy people in charge, produces more wind energy than any other state. In California now, the city of Los Angeles is about 35% renewable power, and they're going to hit 50% within the next 8 years. And so it can be done. You combine that, replacing half of your fossil fuel use with renewables, and then have everybody go with efficient technologies, battery cars, LED lights, and that sort of thing, then you're kind of there on a municipal scale. So to me, Pemex is always going to be around. Well, not always, but I would stop investing in that technology and the exploration of oil, and subsidizing and investing in renewables, right, and efficiencies. So it's transport, get people out of the cars. It's crazy here in cars, isn't it? And more efficient urban transport systems. It costs a lot of money, but at the end of the day, what's the cost of not doing the right thing now? What's the cost to our kids and grandkids? That's what I worry about. So, and we do have numbers on those costs. They're enormous. They're trillions of dollars. So with respect to the different parts of Mexico, ocean acidification is going to be a bigger problem on the West Coast because of upwelling. The waters there are already low pH waters relative to the Caribbean and the Gulf of Mexico. That's probably enough right now, but I think investing heavily in a sustainability program at UNAM, that has to be part of the solution, right? Because that's what that's about, is figuring out how to, once you come up with a renewable power source, what do you do with it? One of the things, like here's an example, for the Gulf of Mexico, for the US, and partly for Pemex, that's an old, very mature oil basin, a place where they recovered oil starting many decades ago. And there are many oil platforms out there that are no longer productive. There's no oil coming up. And by US law, those things have to be taken down and the sea floor treated to bring it back to its original condition. It's super expensive. But what they're talking about now is giving those platforms over to wind farms, and instead of having the oil companies pay to remove the rig, the oil company pays to put a wind turbine or multiple wind turbines on the platform and maintains that. And that's kind of a win-win. The fishermen already know where the platforms are. They've been there for decades. The oil company doesn't have to get rid of this platform. The wind turbines are away from people's backyards. So offshore wind is now the big thing in the US. We even have offshore wind projects underway in California, of all places. So, there are solutions, and so there'll be rigs like that in Mexico. Why not talk to Pemex about putting those up?
Very interesting. Muy interesante. Me gustaría complementar lo que acaba de explicar Rob, diciendo que the way to go es sustainability. Yo estoy aún muy sorprendido. Llevo 8 años en México. Hay mucha inversión, sobre todo en la zona de la Ventosa, en aerogeneradores, pero yo estoy muy, muy, muy sorprendido de el bajo uso de la energía solar. Cuando tenemos un país, sobre todo en la parte del norte, ¿no?, que tenemos tanto potencial solar que no se está utilizando, ¿no? En la parte de mitigación, yo creo que ahí México tiene un gran camino a recorrer, porque realmente es una tecnología perfectamente probada y utilizada en todo el mundo, ¿no? Bueno, no querría... ¿Hay alguna pregunta más? Uy, ahora salen todas las preguntas. Bueno, voy a tomar las dos que me han dicho ahora. Sergei, primero, por favor. Allá. Y ya paramos.
Gracias. We were worried many times about many time about coral bleaching and about how this climate change are gonna kill corals, but right now we have another problems like the emergent diseases that they are appearing, and we don't know why this is happening. In old Florida and Quintana Roo. But what about nutrient measurements or other change in the water system that they are already killing all corals? So now it's not coral bleaching the biggest problem. Now we have another emergent problems that we don't know how to deal with this.
Yeah, I can comment on that. I mean, we had a woman named Greta Aby who's she studies coral disease mainly in the Pacific, and what she's documented is an increase in these just rapidly these viruses that can kill a large tabletop coral in a couple of weeks. The viral front will move 2 to 3 centimeters in a day sometimes. And so she said exactly that same thing to me, like, I don't know why you're working on the carbon system. There aren't going to be any corals left to dissolve. They're being killed by this disease. But at the same time, we'd had temperature recorders out for quite some time, and Jean Albert was there with us one year. And we did notice that the disease happened almost always when the water temperatures were above normal. And they were above normal in part because of global warming. And so there probably is a link to bleaching that, once the coral is in water that's a little bit too warm, and the dinoflagellates, maybe they're producing too much oxygen, and the animal goes into kind of oxidative stress. And that's when this happy marriage between the plant and the animal begins to break down. Hey guys, this isn't so good. Maybe you're going to have to move out. At that time, the coral does become less fit, and it does seem to be more prone to disease. Now, the problem with nutrients and eutrophication, especially if it's accompanied by sewage, if there's any sewage from animals, from pig farms, from humans, you put all of that together and it's this like perfect culture for all kinds of bacteria. And we only know about 1 or 2% of the marine bacteria right now. I mean, that's a huge area where we need microbiology done through genomics. But it turns out once the load of all kinds of clades or different kinds of bacteria rises, then corals tend to get sick. Somehow it makes the viruses more easily able to infect the coral host. And that kind of epidemiology hasn't really been sussed out. But I take your point, and it's a good one. In some places, ocean acidification is not number one in terms of a risk factor for a coral. But you can't do anything about that now anyway, because you don't have your hand on the spigot of fossil fuels. You can through local action and regulations and enforcement, which is often hard, but you can control eutrophication and the input of sewage. And that, where it has been done in parts of the Western Pacific, once Palau went from a really primitive sewage treatment plant to something that's really quite good, like immediately the corals around the sewage outfall started to come back. It was just like that. So I think there's enough evidence that, I don't know, in some of these areas, in the Mayan Riviera, where the big hotels have been built, I don't know when they built them so fast, did they put in proper sewage treatment or is it minimal? So, that's where, and they should engage, people aren't going to come if the reefs are completely dead from disease caused by the hotels. So that's the geopolitical side of things where you have to have to figure out how to make government work for you. Very difficult.
Ok, vamos a agradecer a Rob. Muchas gracias.
Namaste.